All right, sir. You can come in. You can come in. No, where will I? This is 10:23 by 11:30. I'm by 11 o'clock.
11 o'clock. Okay. So you meet the. Hello, class. I think we're
Check. This is where to check the chat.
yeah, children.
No, don't worry. You can speak now.
Speak. Hello, class. Can you hear me, please? Can you respond by chatting? Okay. Evan. Where's the class? This chat. This right here. Okay. So this is the chatting. Yes. Okay, please. We are here for thank you for your patience. We had little issue here, but thank God for the engineers, they've resolved it for us. So physics 103. Please, asked to announce to people offering AMS 103 that you should hold on till 11 a.m. Your class will come up by 11 a.m. That is, those people offering AMS 103. Please, physics 103. Please, can you respond? Are you online? Are you online? Physics 103, are you online? Can you respond, please? Because I want to give you your first attendance code. Please, can you respond by chatting? Are you online? Oh, fine. That's great. Okay. Paul Afolabi, Salaudin. Okay. Okay. I will call the code, your first, because we don't have much time anymore. I will call your first attendance code, and I would love to advise us to be smart with your attendance. Because if you don't have 75% attendance, the system may not allow you to write your exam. So please be mindful of this and be very, very careful. Be smart about it. Now, here is the first code. The first code is AU25W. I take it again. AU25W. 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 That's the code, the first code for today's attendance. And be attentive, because I will soon call the second code, because by 11 we have to round up our class. We have just about 30 minutes more. So be mindful of that. Be attentive. Okay. Now, last time we met, that was on Monday, we talked about elasticity, and that's what we're still going to continue with this morning. And the major slides we dealt with is the slides before us, where we are able to understand that all objects are deformable, and what is responsible for that is the external force. And when you talk of deformation, you are talking of changing in shape or changing in size, or both. And we understand also that material in one way or the other has an internal force to resist this deformation. And when you apply an external force to a body and it deforms, it changes shape or size, when that external force is removed, the material finds a way to restore back to its original shape or size. And such property is what we call elasticity. And two concepts, two important parameters were discussed the last time that we met. We talked about stress and strain. So now this morning, we would love to continue with the teaching. Let me hear your response, please. Are you there? Okay. Thank you, Salaudin, for that putting up the code, the first code. Thank you. So now, okay, let's continue. So today we have just short time. So before now today we'll be looking at we'll start looking at elastic modulus, the fundamental law. Elastic modulus, the fundamental law. And for a small stress, many materials behave elastically. Many materials behave elastically. That is, the strain is directly proportional to stress. The strain is directly proportional to stress. In a simple term, what does it mean? It means when you apply a small force to a material, it deforms slightly. It deforms slightly. And if you double the force within a certain limit, the deformation will also doubles. So that is what we are talking about, that the strain is directly proportional to the stress. So when you double the force within a certain limit, which you will be made to understand what is the limit of that certain limit of stress we are talking about, you soon get to know what is the limit of that limit we are talking about. So when the force is double, the deformation also doubles. And when this force is removed, the material returns to its original shape. This behavior is known as Hooke's law. This behavior is known as Hooke's law. It applies within elastic limit of the material, and that's the limit within the limit I'm talking about. So that limit is what we refer to as elastic limit of the material. So when you apply a force within the elastic limit of a material, it obeys Hooke's law. It obeys Hooke's law. And what is it? It's saying the strain is directly proportional to the stress. And the elastic limit we are talking about is the maximum stress a material can withstand. And when that stress is removed, it will be able to return back to its original position. There's a property of material that is very, very important. We call it elastic modulus. Elastic modulus. Elastic modulus. Elastic modulus is a material property. It's a material property. It's a property of a material, and it's defined as this ratio of stress over the strain. Ratio of stress over the strain is a ratio of what is done, that is by the force, to how the material responds, that is the deformation of the material. So now, what is the physical interpretation of this? The elastic modulus tells us how stiff or rigid a material is. How stiff or rigid a material is. Now, let me see. Let me hear. I believe we are hearing me and you are enjoying. No, this is not 101. This is 103. The physics for biological sciences. The admin AMS 103 will be starting by 11. Please, those waiting for AMS 103, please wait till 11. Your lecture will be coming up by 11. So physics student, please, let's continue. So when you talk of elastic modulus, you are talking about the ratio of what is done to how the material responds to that force, that is the deformation. And when you look at it, the elastic modulus tells how stiff or rigid a material is. The physical interpretation of elastic modulus, when a material has a large elastic modulus value, that when that material is subjected to stress, it undergo a little deformation. It undergoes a little deformation, and such material is said to be stiff. Example of such material that we can have around is steel, ions. So those materials, they have a high value of elastic modulus. But when a material has a small elastic modulus, such a material deforms easily under stress. When it is subjected to stress, it deforms easily. A material that is flexible, such material is said to be flexible. Example of such material is the rubber. And also, you being in biological sciences, either medicine or other biological courses, and even pharmacies, example like our soft tissue in the body, such material has a very small elastic modulus. So elastic modulus is a property of material, which is the ratio of stress to strain of the material. Now, the time of deformation and their moduli. The types of deformation and their moduli. Now, modulus, that's singular. Moduli is plural. So types of deformation and their moduli. We have the first one is the Young modulus, denoted by letter capital Y. Young modulus. When a force acts on a solid, it can deform in different ways. It can deform in different ways. And each type of deformation is described by a specific elastic modulus. So each type of deformation is described by a specific modulus. So when a force acts on a solid, acts on an object, acts on a material, it can deform in different way, and each type of this deformation is being described by a specific elastic modulus. And each of these elastic modulus measures the material resistance to that deformation. So the first type of modulus, a moduli, is Young modulus. That is change in length. Young modulus describe deformation that involves change in length of a material. When you apply a force, for instance, pulling a rod, stretching a rod. So Young modulus is the one that describes the deformation that involves change in length. And it occurs in a material by stretching or compressing. When at time you compress a thing, when you look at a rod, wire, at time, I know some of us in one way or the other, we would have found a cause to do this before. Maybe even some of you, we have seen rubber band before. You stretch a rubber band, you discover that such material, change in length is stretched, and when you release it, it comes back to its normal original position. The modulus that describe that type of deformation, that is change in length, is what we refer to as a Young modulus. And it measures how stiff a material is when it is being pulled or compressed. When you pull a thing or you compress a thing, that parameter, that property that describes how stiff a material is when it is being pulled or compressed is what we refer to as Young modulus. And a high value means the material resists stretching. When the material has a very high Young modulus. It means when you want to stretch it, it will require a very high force for you to be able to stress it. I believe we are enjoying the class this morning. So please, with what we have discussed about Young modulus, I would love you to arrange this material in order of the value of their Young modulus. Steel, rubber, and bone. Steel, rubber, and bone. Arrange them either in ascending order or in descending order with respect to what? The value of your modulus that you think they will have. Either high, low, or relative high. Steel, rubber, and bone. So now when you talk about young modulus, you are talking about deformation in length, and the parameter that describe it is your modulus. Now we have shear modulus. This is a material, this is a property, this is a modulus that talk about changing in shape, change in shape. Shear modulus. Shear modulus describe deformation that involve a change in shape without a significant change in volume. Shear modulus describes deformation that involve a change in shape without a significant change in volume. It occurs when force act parallel to a surface. Now, when you talk of shear modulus, you are talking of a surface area. Now, when we are talking about Young modulus, you are talking about length, just length, one length. But when you are talking of shear modulus, you are talking about an area, surface area of a material. So it occurs when force act parallel to a surface. And the physical meaning or implication of this is that it measures the resistance to sliding or twisting deformation. Sliding or twisting deformation. When you want to twist a thing, twist it. So it is this shear modulus that actually tells us how that material will respond to force that is twisting a thing. So it indicates how well a material maintains its shape. It entails how well a material maintains its shape. Now, I would love that you take the second code, because so that you will be able to submit your attendance. Please, I say you have to be smart about your attendance so that you can have the required percentage of attendance before the end of the lectures. Now, the second code is X75D3. I take it again. S75D3. Salahuddin, please put it up just as you used to do. Is anyone X75D3? S75D3. That's your second code. That is the second code for today attendance. Malik Odejide, steel, bone, rubber. I think you are right. Thank you for responding. Yeah, thank you for responding. So steel, bone, rubber. So steel we have the highest among these three. Still we have the highest Young modulus, followed by bone, then followed by rubber. Thank you for Paul Afolabi. Okay, that's the code. That's the code. No, not X. S. S for Sunday. Yeah. S for Sunday. S for Stephen. S75D3. Not X. Sorry, it's S. Please correct that. X75D3. So let's continue with the class this morning. Okay, now the third moduli, the third type of moduli we have is the bulk modulus. Bulk modulus. bulk modulus describe deformation involving a change in volume due to uniform pressure. When a body is subjected, a material is subjected to equal pressure in all directions, the body is tend to deform. It tend to deform. It tend to deform. And the modulus that describe this deformation is what we refer to as bulk modulus. Is what we refer to as bulk modulus. So these are the three type of deformation, and their moduli that we can have in a material. And for bulk modulus, when you have a high bulk modulus, if a material has a high bulk modulus, it means that material is hard to compress. It's hard to compress. Let me see the second code. I believe we got the second code. Yeah, Sharif Ali is, yeah, you are right. S75J3. That's the second code. Oyedele Oyewale, thank you. That's correct. Paul Afolabi, that's correct. Please, Samuel Abidoye, no, that is not correct. That is not X. It's not X, it's S. S for Stephen. 75D3. So thank you. Please be mindful of your attendance, please. Be mindful of your attendance. Okay, so I said, when a material has a high bulk modulus, it means that material is very hard to compress. Some of us, we buy a bread, a loaf of bread, a long one, and we just put it between our two hands and compress it. And you discover that you compress it and squeeze it into either your small cooler or small bag you want to put it. It is because the bread has a very low bulk modulus. That is why it is easy for you to compress. Now, let's continue. So we want to pick the first one, the Young modulus, tension, stress, and strain. Young modulus, tension, strength, and strain. Hope I'm not too fast for us. Hope you are catching up. Let me see. Please, hope I'm not too fast. Are you getting it? Are you getting the class? This is Physics 103. Please, this is not 101. It is Physics 103. Physics for biological sciences. Are we getting it, please? Are you with me? Are you? Yeah, thank you. Malik, Odejide, Salau. Okay, yeah. So now let's continue. Let's now go back to the first modulus, which is Young modulus. We'll be talking about Young modulus, tension, stress, and strain. For a long bar, just as you can see in our figure here, look at the figure here. That's a bar. That's a bar with cross section A. A bar with cross section A clamped on the edge of a table. Clamped on the edge of a table with its length held high, held substrate high. This is the original length of the bar, and it has a cross section area of A. Now, there's this force that is being applied at the other edge of the rod, pulling the bar, or let's say the bar, yeah, pulling the bar on this direction. So by the reason of this force, the bar extends by d delta L. So it extends by this delta L. So you can see that this material, this rod, has gone through a kind of deformation by the reason of the applied force. And the deformation is just by increasing in length. It's just by increasing in length. And with what we just discussed, you discover that such deformation is what Young modulus describe. Such deformation is what Young modulus describe? It describes a deformation by changing length. Deformation by changing length. So Young modulus describe how a material responds when it is stretched by a pulling force. It applies to lumbars, wire, even bones in the body. We in biological science, we should be mindful of this. We should be mindful of this. So for this long bar with cross-section area A and initial length, its initial length was L high. The tension stress is the force over the cross-section area. The force over the cross-section area. And the tension strain is change in length over the original length. Change in length over the original length. And from our definition of Young modulus, we say it is what? Stress and stress over the strain. So the Young modulus for this material now that is here, it will be what? It will be tension stress over the tension strain, given by this formula. Given by this formula. So now, I will love that I give us the third, I will give us the third code very soon for us to log those and send it and submit. Oh, okay. We are getting it, sir. Thank you. Please, the slides. Yeah. Now, rubber is easy to expand. That is why it has low modulus, and the reverse is for the steel. Yeah, thank you, Balogun. Yeah, you get the point. You get the point. Now, I'm glad that you are getting it. Thank you. So I will soon give us the last code for today so that you can submit before 11, before the system log you out. So be attentive. I will soon give it to you so that you can submit. So, okay. Now, let's now look at key observation for Young modulus. Key observation for Young modulus. Key observation for Young modulus. So it will be on this note that we are going to round up on this load that we are going to round up the class today. But let me give you, so we'll discuss this key observation for Young modulus. Key observation for Young modulus. Young modulus describe how a material stretched when a tension force is applied, and from the experiment and theory, several important observations can be made. The first observation is that for a given fixed force, the extension is proportional to the length. That's the first point. Please be mindful of this. For a given force, for a given fixed force, extension is what? Is proportional, directly proportional to the original length. What does this mean? It means when you are giving a material with a given cross-section area and force is applied, the longer that material is, the more the force will stretch that material. What am I saying? I say a longer bar stretches more than a shorter one. A longer bar stretches more than a shorter one. If two wires of the same material and thickness are pulled with the same force, the longer wire will have a greater extension than the shorter one. And that is the first observation for Young modulus. So extension of a material is proportional to its original length. Extension is proportional to its original length. The second observation is that applied force is proportional to the cross-section area. That's the second observation. For a given strain, the applied force is directly proportional to cross-section area. Let me give us the last code for today. Let me give us the Joshua Adekami. Thank you for that. You say we are getting it. That's nice. So let me give us the last code for today. The last code for today. I immediately drop it. Immediately you get it. Please just drop the 3 code and submit, so that before I round up the class, all of you should have submitted your attendance. So please, the last code is EV5CX. 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 X now. Yeah. Thank you, Oba_90. Yeah. EV5CX. Please start submitting now. Yeah, thank you. Emmanuel Kolapo. So please submit now. Submit, and let me have your response if you have done that, if you are successful. If not, if you are not successful, let me know so that I can contact the engineers will help us out so that you can submit your attendance for today. Please, once you submit the 3 and it's successful, let me just know by saying done, so that we'll know that submission is done, please. So now, the next observation that we are talking about is that force is directly proportional to the cross-section area. It produced the similar fractional extension in a thicker bar. What are we talking about? When you apply a force, when a bar, that is, what we are saying is that a bar with a larger cross-section area is stronger and more resistant to stretching. When a bar has the higher the cross-section area value of that material, the more difficulty it will be for that material to be able to be stretched. So the force is directly proportional to the what? To the cross-section area. And of course, each material has the value. It has a value for Young modulus. So if you look at the table given to us there, you'll see substance, that is different kind of material. You see tungsten and steel, copper, brass, aluminum, glass, and so on. You see there's a specific value of a word of Young modulus that is given here. So this will be where we be rounding up today, but I would love to give us a question for us to respond to. So please submit your attendance, please. Submit your attendance, please. Submit your attendance. Submit your attendance, please. So let's take this question. Please, can you write this question down so we solve it before we have just 3 minutes or 2 minutes more. Please write this question down. A bone of length 2 meters. A bone of 2 meters, a bone of length 2 meters and cross-section area of 1 times 10 raised to the power minus 6 meters square. A cross-section area of 1 times 10 raised to the power minus 6 meters square is stretched by a force of 200 Newton. Is stretched by a force of 200 Newton. If the extension produced is 2.10 raised to the power minus 3 meter, if the extension produced is 2.10 times 10 raised to the power minus 3 meter, calculate the Young modulus of the wire. Please, you have just 2 minutes more. Please submit before 11. By 11, the system will log it out. So you have about 2 minutes more. I take this question again. A bone of length 2 meters and cross-section area 1 times 10 raised to the power minus 6 meters squared is stretched by a force of 200 Newton. If the extension produced is 2 multiplied by 10 raised to the power minus 3, calculate the Young modulus of the bone. Thank you. See you on Monday. Please kindly submit your attendance. Thank you. Yeah, have a wonderful weekend. Yeah. So just, I think they are responding.
Yes, they are responding.
Done.
Check. you can ask if they are on.
Slide.
So no, you be right. You be right. You are live. You can meet.
Hello, good morning. Good morning, everyone. AMS 103 students, are you around?
It's 103.
Good morning. Yes, this is a MS 103 class. AMS 103. This month is very sensitive. I don't need the mouse. Okay, they are here.
Almost have to restart. No,
Okay. Sorry for the little delay. Good morning, everyone. AMS 103. How was your matriculation? Congratulations on your matriculation. You are now bona fide students of Obafemi Awolowo University. We are so sorry for the delay. So let's start our class. In our last classes, we have defined, we all know the definition of computer. What is a computer? A computer electronic device that receives data, that receives input, processes data, stores information, and produces output according to a set of instructions. We are all familiar, I believe we are all familiar with the definition of computer. The word computers come from the word compute. It means to calculate. So we can say a computer is a calculating device, but that is not the exact definition of a computer. It is an electronic device that receives input, processes data, shares information, and produces output according to a set of instructions called programs. Computer has the physical structure and the software, also software. When we are talking of the physical structure, we are talking about the hardware, that is the physical structure. And we also have the software. We provide instructions to the computer ranging from operating systems like Windows or Linux and the rest, instructing the computer to perform some specific task. So we're examples of computer. You have your desktops and your laptop, smartphones and tablets, ATM, smart TVs, and car onboard system, and so on. What are the basic functions of a computer? That is the computing process. Computer perform 4 main functions: input, processing, storage, and output. By input, computer receives data. We all know what data have: unprocessed, raw. Then we have the processing, that is the manipulation of data via calculation or logic. Then we have storage, that is when the computer saves what it has processed. And we also have the output, whereby the computer displays the result. So these operations enable diverse uses, from input, let's say from simple calculation to even complex calculations. So the computing process involves the input, which is, we have accept data here, where you input your raw figures, your facts, your symbols that has not yet been processed in their raw form. Then processing, that is the manipulation of data via calculations, and logic. Then you have your storage, where the computer stores what it has processed, and output, where results are displayed. What are the characteristics of a computer? We are all familiar with the characteristics of a computer. I think it has been taken in the previous class. We have high speed. Computers are very fast. Computers have unbelievable speed. For instance, now, computers can perform billions of instructions per second via modern processors. Then computers are diligent. By diligence, it means the computer can perform various repetitive works without getting tired. In computer process, when you give same instruction repetitively, we call this looping. Then accuracy is also one of the characteristics of computer. Computers are accurate. It means they remain consistent unless faulty inputs occurs. Other than that, computers will give you accurate results, ensure reliable output for repetitive tasks. Then computers are reliable. They have the reliability stems from structured design, minimizing error in controlled environments. For a microprocessor chip, for instance, is said to have a life of 40 years. So what are the roles of computer in various fields? We can use computers are used in various fields. For instance, in scientific research, computers are acknowledged to be fundamental pillars of modern science, acting as a powerful tool for simulation, modeling, and the rest, and data analysis at a scale that is impossible for human. So computers are very useful in scientific research. The computers make efficient parallel processing, which break down enormous problems, such as when you are predicting hurricane paths now. In some parts of the world where they have hurricane occasionally, computer system can help scientists to predict the path that the hurricane will follow. Then in business, we use computers in various places like banks, airports, in the stock exchange, hotels, export houses, even in governments, and some other businesses. In private businesses, no matter what you do, you can make use of computer to enhance your business operations. Then in space operation, computer is also very useful. It is known as the essential brain of modern space technology. It enables autonomy, precision, and communication across vast distances. For instance, now, with advancement in radiation hardening hardware and AI, computers now allow spacecraft to operate autonomously in deep space, where real-time communication with Earth is almost impossible. Then in data communication, computer is known as the global connecting tissues. It allows people to connect from various parts of the world through networking, hardware, and protocols. Then in medicine, computers are very, very useful in medicine. They are used in hospitals, nursing homes, clinics, even for diagnosis. Also for maintaining medical and health records, prescription writing. For instance, your X-ray machine is a type of your X-ray, CC, all those other machines that they use for different types of scan, like MRI, CT scan, and the rest. Then in the area of teaching, for instance, now this class is being done via the computer. So we also have some other online courses, such as you have your Coursera, your Udemy. All those ones are also very useful. They are e-learning platforms that enable people to learn via the computer system. Then in engineering, computer-aided design is used for designing and modeling. Then we also have the computer-aided engineering, which allows to stimulate physical behaviors like stress and heat. Then we also have computer-aided manufacturing that generates instructions for machines like the 3D printers and CNC system. So those are some of the areas where we make use of computer. The list is not exhaustive. So let's look at the limitation of computer. As good as computers are, computers also have limitations. Here we have no IQ, no feeling, no decision-making ability, and they are also user-dependent. Let's take the limitations one by one. No IQ. The computer does not have, it possesses no intelligence of its own. Its IQ is 0. It does not have IQ. As at today, we don't know what will come up tomorrow, but as at now, the computer has no IQ. The IQ is 0. It has no intelligence of its own. Because the computer is a machine, it does not have innate cognitive or emotional faculties. So its IQ is 0, meaning it cannot initiate tasks. It cannot think creatively, or it cannot understand context beyond what is programmed in the system. So all operations are simply determined by the instructions provided by the user. The computer does not have any initiative of its own. Then the computer has no feelings. Computers are devoid of emotion. They are purely logical machines. They cannot experience empathy. Computers cannot experience pleasure or frustration, and they cannot also employ intuitions because they don't have feelings. So the absence of emotion directly leads to another core limitation of the computer system, which is no decision-making ability. Computers cannot make decisions because they don't have knowledge and judgment ability. They have no true decision-making or judgment ability. They can execute complex comparison and follow decision trees programmed into them, but they cannot make independent judgments. they cannot exercise discretions. Computers cannot understand the ethical and situational nuances that often inform human choices. Then computers are user dependent. Computers fully depend upon the user. They cannot do anything without instructions. They only follow the instruction given to them by the user. A computer is entirely incapable of performing any action or solving problem without explicit instructions, data, and defined parameters provided by human operators. So we have some other limitations of the computer. For instance, it has algorithms and theoretical limits. Then the garbage in, garbage out principle too. It is whatever you input into the computer that the computer will bring out. The quality of output is entirely dependent on the input. Then we have some other limitations of the computer, such as the physical and engineering constraints. For instance, the computer has finite resources. That is, the memory, the storage and processing speeds are finite. Though there are improvements over the years, but up to now they are finite. Then the power consumption and heat too. As engineers, as they are trying, and let me say the computer scientists, as they are trying to provide faster processing, to develop computers with faster processing capability, there are some barriers, such as enormous energy demand. So that is one of the limitations of a computer. Then lastly, the computer does not have any physical experience. So let's move on to, okay, application of computer in business. Today, it is inevitable to use computer in business transactions. Though in the past, it was believed that computers are only meant for some certain types of businesses and in some certain types of organization. But now, this belief has been overtaken by continuous change in technology, which makes every aspect